In this video, we'll look at some other op-amp circuits that you may find useful. Our first circuit will be a current to voltage converter. If we want to measure a current, then ultimately we need to convert this into a voltage which we can then feed into a microcontroller or a computer. So if we have a current here, the easiest way to convert that into a voltage is to pass that current through a resistor and then measure the voltage drop across that resistance. So we have V equals IR, so we can get a measure of the current that way. The problem is, if the device supplying the current doesn't have enough power, it is not able to push current through this resistor effectively, and therefore that will limit our output voltage. A better way to do it is to use an op-amp in a current to voltage converter circuit. In this circuit, we have got negative feedback via this resistor going to the inverting terminal of the op-amp. Our device here is supplying current. We know the op-amp doesn't sink any current, so all this current goes around the feedback loop, and we get the transfer function of V out equals minus the current times the resistor. And in this case, the op-amp is supplying the power to be able to push that current through the resistor. This circuit is the Schmitt trigger. It looks very similar to an inverting amplifier arrangement. However, in this case, the feedback is to the non-inverting terminal of the op-amp. So in this case, our golden rules aren't going to apply. For this circuit, the op-amp is effectively acting as a comparator, so it's either going to be plus Vs or minus Vs on the output. So for the first case, we'll consider is plus Vs. So we'll say our output is currently at plus Vs, and what we want to do is work out the potential at this point here. So the potential here is given by our input voltage V in plus a fraction of this potential difference between the input and the output. So it's V out minus V in, and a fraction of that as the potential divider is going to be R1 over R1 plus R2. And if you remember, V out is currently at plus Vs. So we get the potential at the input of the op-amp is this. If we rearrange that to get this side here in terms of V in, then we can rearrange to that, which leads to that and gives us this term here. For our output to switch to minus Vs, then the input voltage has to drop. So if we go back to our circuit, the output will go to minus Vs, so that will go to minus Vs when this potential here, so the potential at this point, drops below the potential at this point. So this point is at earth, so this is 0 volts, so therefore this point here has to drop below 0 for this output to switch to minus Vs. So if we put 0 in this equation, which is that equation, then we put 0 in here, and this gives us V in equals minus R1 over R2 Vs. So when V in drops to this value, our output voltage will switch to minus Vs. If we now go back and look at this, so this is now minus Vs. If we want this to now switch back to plus Vs, so it's currently at minus Vs, if we wanted to switch back now to plus Vs, then this potential point here is going to have to increase until it gets more than 0, so it's more than this point here. However, our Vs here is now negative, So our transfer function has become this term because Vs is currently negative, and therefore this is going to switch back when our V plus is 0. And if we work that out, we get V in is R1 over R2 minus Vs. So it'll switch from positive to negative when V in is minus R1 over R2 Vs. And then it'll switch from negative to positive when V in is a value of R1 over R2 Vs. So if we plot this out, what we find is we have hysteresis in our circuit. So if our input voltage is increasing, then the output only switches when the input has reached this value. However, if the input is decreasing, then the output switches back at a different value. So an example of where that might be useful is we'll have a look at debounce in switches. So imagine we have a switch here, and when we close that switch, we want to register it as being closed. So we're going to count how many times this switch is closes during the day. So when we close this switch, there'll actually be a mechanical effect where the switch will close, it'll bounce slightly, come open again, close, open, close. So when we actually throw this switch, it'll register a few contacts. So if we just measure this part directly, if we just look at this part directly, what we will get is this as an output. We'll see the switch bouncing on and off until it settles. So if we were counting these switching events, we'd actually measure multiple events for the one switch, for the single switching event. So what we do next is we add a low pass filter. And what the low pass filter does is essentially smooth out this switching effect. So we've got a capacitor here. So when we close this switch, it'll start to... So when we close this switch, it's connected to ground. So any voltage on this capacitor will slowly drain away. When the switch opens, this positive voltage supply will start charging it again. So if we add a filter onto this, what we see is the capacitor is charged. When the switch is closed, it starts to discharge. The switch is bounced open again, so it starts to charge, discharge, etc. So that's how it improved our situation, because if this is our threshold point for counting the number of switching events, we can see we've only now recorded 2 switching events where the output is high at this point and at this point. So we've improved the situation, but we still haven't correctly counted the one switching event that's actually happened. So what we now do is we put in our Schmidt trigger after this, and this adds hysteresis. And what that does is, rather than give us our 1 point for switching, it gives us 2 points for our switching event. And it'll register a switching event if it goes below this line, but it won't consider the switch as being open again unless it goes above this line. So now, although our signal is doing this through our filter, so it registers a switching event at this point, but it ignores it at this point because it hasn't reached this upper line, and therefore it hasn't considered it as being reopened to switch. So going through the full low pass filter and Schmidt trigger, these originally 4 pulses we got out from our bouncing for our switch is now down to just 1 output from our Schmidt trigger that registers the 1 closing event. This is an example of an oscillating circuit. So again, as you notice, we have got positive feedback. So the output is going to be either the plus Vs or minus Vs supply voltage. So what we'll do is we'll consider this currently as minus Vs. This is at earth, and then depending on these resistor values, this is going to be a fraction of that. So we will say if that is at minus 10 volts, then this resistor ratio is going to give us minus 7.5 volts at this point. So our output is currently at minus 10 volts, which is here. If we look at the voltage at the inverting terminal of the op-amp, and we'll say it's currently at this value, because this is at minus 10, what's going to happen is we're going to get current flowing, which is going to slowly charge this resistor up, and it'll charge it up to minus 10 volts. So we'll find this voltage at this point is slowly getting charged to minus 10 volts. So we're going to trace this line down. However, when it gets to, we said minus 7.5, so if this was, let's say, minus 7.5, when this gets to just below minus 7.5, this voltage here is going to be less than this voltage here, and therefore this op-amp, which is acting as a comparator, is going to switch to plus 10. So the output is going to suddenly go from minus 10 volts to plus 10 volts up here. So this is now at plus 10 volts. So if I just clear that screen. So now we've got this with this point on the graph. We had plus 10 volts on the output. This is currently at minus 7.5 volts. What we're going to get now is current flowing to start charging this capacitor up to 10 volts. So this capacitor is going to start charging. We're going to follow this curve up. And this is going to slowly increase and try and get to 10 volts. However, the point here is now at plus 7.5 volts. So when this voltage here exceeds that plus 7.5 volts, this part, or this input's going to become the greater, and therefore the voltage will therefore switch again back to minus 10 volts. Therefore the output will go back to minus 10. So this circuit continually oscillates between the plus and the minus output supply. So it'll either go from minus Vs to plus Vs on its output, and that switching event will depend on the capacitor value and the resistor values to give you this reference voltage here. So this circuit gives you effectively a timing pulse from what you can use in your circuit. Now you can design a circuit such as this to give you this functionality. However, with most circuits today, you can actually buy them pre-packaged. So if you do want an oscillating output, the standard chip to buy would be a 555 timer. So it works in a similar way, but all the electronics is packaged already up in a chip. And in terms of how fast you want these oscillations, that is your choice, because each of these chips comes with effectively a design equation. So you'll have to look on the data sheet for your specific chip you've bought. But for a given frequency what you want, you just choose suitable components, and these get connected externally to the chip. And then this gives you your pulse signal, what you want, that you can use for timing. Our last circuit we'll look at in this video is for amplitude detection. Imagine we have an AC signal and we wish to detect the amplitude of this. So if I just sketch this up. So there's our voltage against time. We've got an AC signal. We wish to find this amplitude. We cannot measure the average, so we could measure the average either using an integrating amplifier or low-pass filter. However, we don't have this option, because if you look at that signal, if you find the average of this, then that is just going to average to 0. So that is not an option. We could try peak detection. So what a peak detection circuit would do is find the highest point in this. So it might be there, say, for example, and then that might potentially work. However, if we've got a signal with a bit of noise on it, so it actually looks like that, then the peak detection is going to measure the highest point of the noise and not the value we want. So what we could do is rectify the signal and then find the average. So when we say rectify, what we're going to do is change this signal. So if I just delete that. So we have this signal here. When we rectify it, what we're going to get is just convert it all to positive. Now we can then integrate that, or what we could do is low pass filter it, because what a low pass filter will do is find the DC value or the average value of that. So if we low pass filter that signal, we will find the average value. Now although that isn't the peak value, that average value will be directly proportional to the peak value. So we can work out the peak value using this average value. So a good way to do amplitude detection is to rectify the signal and then low pass filter it in order to get an idea of the amplitude of the original signal. So that's our aim, is to rectify a signal in order to get the amplitude detection. So the traditional way to rectify a signal is to use a diode bridge. So I'll refer you to Wikipedia for that. So a diode bridge is essentially you have an AC signal coming in on this side of the bridge. It passes through diodes and then you take the output off the other terminals. And what that does is give you rectification similar to that. The slight downside of that is diodes have got a very slight voltage drop across them. So your signal will be rectified, but it'll probably look something like that. So it would work, but there'll be a slight error involved because of this loss, the voltage drop across the diode. However, if we go on to the next slide, there's a lot of electronics experts out there, and there's a lot of good circuits. So if you sort of do a literature search or look around, there's lots of circuit ideas that are very useful. So you don't necessarily have to go and design your own circuit. You can use a circuit from somebody who's a lot more experienced at doing this. So if I can copy that data sheet, I will leave a copy of the data sheet on Canvas. But if you look at this data sheet, what you have there is a circuit that will give you a rectification of the signal, which looks like this, and it'll do it accurately so you won't get the voltage drops. So it's an op-amp circuit that will rectify and do it accurately. So you will need to use good quality components to do this. So when we do this practically, rather than use 741s, we use higher performing op amps, the TL074. But by doing that, what we can do is rectify the signal, pass it through a low pass filter, and then that'll give us a DC level that is proportional to amplitude. Okay, so the point of this slide, so I've included in there, so that's your circuit and that's your rectification. So the point of this part is to show you an example circuit that we will use in the next video, but also to demonstrate you do not necessarily have to go and design all the circuits you need. There's a lot of data sheets out there, especially when you buy components, on examples on how you sort of configure the circuit and make the circuit up. So utilize these resources and they'll give you a lot better performance than you would get from designing your own circuits. So I recommend, when you've got the option of using somebody's expertise to build your circuits, then you do that. I just want to finish this video by discussing digital alternatives. So we have looked at circuits to do jobs, but we can actually do this in software. So here's some examples. We did a debounce circuit using a Schmitt trigger. So when a switch is closed and there's mechanical bounce, we used a low pass filter and then a Schmitt trigger to just record the one bounce rather than the multiple bounces from that mechanical contact. This is also quite easy to do in software. So if you're counting these pulses in say an Arduino, then when you detect one pulse, all you need to do is sort of delay, so you don't do any more readings for a certain amount of time, and then that would effectively get rid of the debounce. So that's quite an easy software solution. Amplitude detection, again, could do that in software. So what you'd need to do is sample your signal quickly enough that you are sure to record the peak of that the sine wave passing through. So if you've got a quick enough digitizer compared to your signal frequency, you could actually measure the amplitude in software. And then in terms of the 555 timer, microcontrollers have got timers in them, so you could set up a microcontroller to give you your timing pulse rather than use a separate chip. This is not trivial. This is a bit more involved than the programming we've been used to. So it's a little bit more complicated than I'm making it sound, but it is possible. So I've given you a reference there if you wanted to use an Arduino as a timer. So there are digital alternatives to all these circuits, or a lot of these circuits. So it's just something to bear in mind. So that concludes this video. And in the next video, we'll have a look at trying to design our own sensor for distance ranging.